Wars are fought with weapons, but they are won with information. Beneath the noise of battle, a quieter war unfolded, one of ciphers, mathematics, and machines. It was a war where silence meant victory and secrecy meant survival. The Second World War became the first conflict where intelligence was mechanized, where human logic merged with circuitry to read the enemy's mind before he acted. At the heart of this invisible front stood code breaking. Every army and navy in the world relied on encrypted communication. Orders, coordinates, and plans were transmitted through networks of coded messages. The Axis powers believed their systems unbreakable. Germany used the Enigma machine, an electromechanical device with rotors and plugs that generated billions of cipher variations. Japan used Purple, a complex system of electrical switches that changed patterns daily. To the enemy, these machines promised secrecy. To the Allies, they presented an equation that had to be solved before the war could be won. The task fell to mathematicians, linguists, and engineers, the thinkers of Bletchley Park in Britain and Arlington Hall in the United States. In small wooden huts filled with noise, smoke, and tension, they faced a problem larger than any before it: to break a machine-generated code faster than messages could be sent. Brute force by hand was impossible. The solution was to build a new kind of machine, one that could think through possibilities faster than a human brain. In Britain, this effort produced two breakthroughs. The first was the Bombe, designed by Alan Turing and Gordon Welchman. It tested rotor combinations in the Enigma system by logical elimination. The second was Colossus, the first programmable electronic computer, created by engineer Tommy Flowers to attack the German Lorenz cipher used by High Command. Colossus read paper tapes at 30,000 characters per second and performed logical operations electronically, a leap beyond mechanical calculation. It was the moment when code-breaking became computing. Across the Atlantic, American cryptanalysts tackled the Japanese naval codes, culminating in the decryption of JN-25, which revealed Japanese plans before the Battle of Midway. That intelligence turned the tide of the Pacific War. Later, the Purple Machine's secrets gave Allied strategists deep insight into Japan's diplomacy and military structure. Each decoded message was a silent battle won. Every intercepted signal meant convoys rerouted, ambushes avoided, submarines destroyed. The scale of these operations was enormous. At its peak, Bletchley Park employed more than 10,000 people: mathematicians, typists, engineers, and clerks. Their work was divided into sections that specialized in naval, air, or diplomatic ciphers. Each message passed through rooms of machines, from punch-card sorters to paper tape readers, as analysts pieced together meaning from fragments. The process combined human intuition with machine speed, an early form of human-computer collaboration. The secrecy surrounding these efforts was absolute. Even among the participants, few understood the full scope of their mission. Most believed they were engaged in routine analysis. The truth was known only to a handful of commanders and intelligence officers. After the war, many veterans of Bletchley Park never spoke of their work for decades. The entire operation remained classified until the 1970s. The results, however, were decisive. Historians estimate that Allied code-breaking shortened the war by at least 2 years. It neutralized the U-boat threat in the Atlantic, exposed enemy troop movements, and allowed the Allies to anticipate attacks before they occurred. It turned intelligence from a passive resource into an active weapon, predictive, preemptive, and precise. But beyond victory, the codebreakers created something enduring: the architecture of modern computing. The vacuum tubes, relays, and logic circuits of Colossus formed the blueprint for the digital revolution that followed. The mathematical theories developed for cryptanalysis became the foundation of computer science. The same logic that decrypted Enigma would later guide the birth of algorithms, programming languages, and networked communication. In the war's shadow, the first sparks of the information age were lit. The battlefield had shifted from geography to data. The Allies had built machines not just to win a war, but to invent a future. The codebreakers of the 1940s worked for silence, but their machines gave voice to the modern world, a world still shaped by their invisible victory. The story of code-breaking was as much about human patience as technological speed. Every message that reached Bletchley Park or Arlington Hall arrived as noise, a meaningless stream of letters that concealed life and death decisions. The codebreakers' task was to turn that noise into knowledge before the knowledge turned into action on the battlefield. It was a race against time, fought with logic, intuition, and machines that barely existed before the war. At Bletchley, the day began before dawn. Intercept stations scattered across Britain, Y stations, captured enemy radio transmissions and relayed them through secure lines. The signals arrived on paper rolls, punched or written by hand, and were sorted into categories: naval, air, army, diplomatic. Linguists grouped similar phrases, analysts searched for patterns, and mathematicians tested theoretical weaknesses in the cipher systems. It was organized chaos, guided by intellect. Each room specialized in a single fragment of the puzzle, none knowing the full picture. Alan Turing's team focused on the German naval enigma, the most complex version. They used statistical reasoning to identify cribs, or probable words hidden within encrypted text, weather reports, headings, routine phrases. Once a crib was found, it became a thread to pull. The bomb machines, standing in rows and humming with mechanical rhythm, tested hundreds of rotor settings per minute, eliminating impossibilities until a solution emerged. When the correct alignment was discovered, an operator shouted the signal phrase that meant success: "Stop the drums." A day's worth of German naval traffic would then pour open like a flood. The intelligence derived from these decrypts was codenamed Ultra. It was passed to military commands under strict secrecy. Field officers never knew its source, only that it was from a special intelligence. This anonymity protected Bletchley's existence, but also limited how freely commanders could use the information. Nevertheless, Ultra shaped every major campaign after 1941. It exposed the movements of U-boats, revealed Luftwaffe deployment schedules, and predicted enemy logistics. The Battle of the Atlantic was won not just by ships and planes, but by logic tables and typewritten messages from a quiet English estate. In the Pacific, similar efforts unfolded in parallel. American cryptologists, including William Friedman and Agnes Driscoll, worked to break Japanese systems like JN-25 and Purple. They built analog machines called Purple analogs that mirrored Japan's encryption device. These machines, coupled with tireless hand analysis, uncovered Japanese naval intentions before Midway, allowing Admiral Nimitz to position his fleet perfectly for ambush. That victory changed the balance of the Pacific. Code-breaking's progress also demanded new methods of data handling. Each intercept produced thousands of punched cards, sorted by frequency, length, and pattern. This reliance on mechanical data sorting led directly to the design of automatic counting and tabulation machines, precursors to computers. Technicians modified Hollerith tabulators, once used for the census, to manage cryptanalytic data. Mathematics had become machinery. The atmosphere at these centers mixed secrecy with exhaustion. Long shifts under dim light, endless paper streams, and the constant awareness that a missed pattern could cost thousands of lives. Yet morale remained high because every success was immediate and tangible. When decrypted intelligence warned of a submarine attack or exposed a bombing raid, lives were saved the next day. Codebreakers rarely saw battle, but they felt its pulse in every signal they intercepted. As machines like Colossus appeared, the balance shifted from manual labor to electronic speed. Logic circuits replaced fingers and pencils. For the first time, humans built a device not to calculate numbers but to interpret logic, a machine capable of decision within limits. Each victory in decryption pushed computing closer to autonomy. By the war's final year, the partnership between human analysis and machine computation had become seamless. Analysts posed questions. Machines tested answers. Results came faster than any enemy could adapt. The codebreakers had turned the invisible into something measurable, predictable, and conquerable. Theirs was a war of intellect, a war that proved information itself could be a weapon sharper than steel. By the end of the war, the silent intelligence war had become one of the greatest achievements of the modern age. The codebreakers had done more than decrypt enemy messages. They had built the foundation for the computer age. In the dim rooms of Bletchley Park and Arlington Hall, humanity took its first steps toward thinking machines. The logic that cracked ciphers would soon drive transistors, software, and the entire digital revolution. Colossus, completed in 1944, stood at the center of that transformation. It filled a room, glowed with thousands of vacuum tubes, and read paper tape at blinding speed. Its task was to break the Lorenz cipher, used for Hitler's most secret communications. The machine compared streams of code, calculated probabilities, and identified repeating patterns invisible to the human eye. In doing so, it performed logical operations, the very essence of computation. Its creator, Tommy Flowers, had built the first electronic processor, not for science, but for war. Across the ocean, American engineers followed a similar path. The National Cash Register Company, Bell Labs, and Harvard University built electromechanical calculators to aid code breaking and logistics. The Harvard Mark I, designed by Howard Aiken, could perform automatic sequences of operations, another precursor to the computer. What linked all these machines was purpose, to accelerate thought, to process more information than a human could. The war's need for speed had forced the birth of automation. The end of hostilities revealed how deep that change had gone. The Allies had not simply broken codes, they had invented a new relationship between man and machine. Mathematicians became programmers, their logic converted into circuits. Cryptanalysis became computation. The distinction between intelligence and information vanished. After 1945, many of the scientists who had built wartime machines moved into post-war computing. Alan Turing proposed theoretical models for universal computation. Engineers who had worked on Colossus designed the systems that led to ENIAC and UNIVAC. Intelligence agencies quietly applied electronic analysis to surveillance and data management. The infrastructure of code breaking became the architecture of modern information systems. But the human element remained central. The codebreakers had learned that even the most advanced machine required intuition. Every cipher revealed not only mathematical structure but human habit, repetition, error, routine. Understanding the enemy's psychology was as vital as understanding his encryption. This union of logic and empathy defined intelligence work in the decades to come. The secrecy around these achievements persisted long after victory. Colossus was dismantled, its existence hidden for 30 years. Official histories barely mentioned Bletchley Park. Only in the 1970s did the truth emerge, that a handful of mathematicians and engineers had quietly altered the course of the war and the course of history. Their success had shortened the conflict, saved millions of lives, and introduced the world to the power of computation. In hindsight, the code-breakers' victory was more than military. It was civilizational. They proved that knowledge could triumph over force, that equations could undo empires, and that silence could shape the future. The machines they built no longer exist, but their logic runs through every circuit, every processor, every screen. In the war's aftermath, the weapons of secrecy became the tools of progress. The first computers, the first algorithms, the first glimpses of artificial intelligence, all were born from the need to read what others wished to hide. The war had forced humanity to create machines that could think faster than men, and in doing so, it had made thought itself the new battlefield. The code-breakers of the 1940s never sought glory. They lived and worked in silence, knowing that victory depended on secrecy. Yet their legacy is everywhere, in the rhythm of data, in the hum of servers, in the unseen logic that governs the modern world. They had fought without guns, won without headlines, and built a future their enemies could never imagine. When American bombers took flight over Europe, their power depended not just on altitude or payload, but on precision. Dropping bombs from 20,000 feet was like throwing stones in a hurricane. Wind, speed, and gravity turned every strike into a guess. The U.S. military needed a way to turn chaos into calculation, to make bombing a science instead of an art. The answer came in the form of an optical machine, so advanced it was once described as the secret weapon of victory. It was the Norden Bombsight, the mechanical brain that promised to make every bomb fall true. Developed by Dutch engineer Carl Norden, A devout and methodical man, the bombsight began as a peacetime invention. In the 1930s, the U.S. Army Air Corps adopted it for high-altitude daylight bombing. Inside its compact steel casing was a gyroscopically stabilized analog computer. The bombardier would enter altitude, airspeed, and wind direction. The device then calculated the precise release point. Through its sight, the bombardier tracked the target, and the Norden automatically adjusted the bomber's course. It was both telescope and computer, part optics, part mechanism, and entirely revolutionary. The Norden was treated with near-religious secrecy. Every bombsight was guarded, locked under armed watch when not in use. Bombardiers took an oath to protect its secrets, and in the event of a crash, they were instructed to destroy it with a pistol or grenade. The United States believed it held a device that could deliver surgical precision, bombs through a pickle barrel from 20,000 feet, as propaganda boasted. While that phrase was optimistic, the Norden did represent a leap forward in aerial targeting. Inside a bomber, the bombsight became the command center of the mission. During a run, the pilot turned control over to the bombardier, who steered the plane using the Norden's linked autopilot system. Through the eyepiece, he saw the world shrink into crosshairs, bridges, rail yards, and factories, targets reduced to geometry. As he stabilized the image and the system completed its calculations, a small motor automatically released the bombs. The process lasted only seconds but determined the outcome of entire campaigns. In practice, precision was elusive. Weather, flak, enemy fighters, and human stress all affected accuracy. Over Europe, bombs rarely landed exactly where planned. Yet compared to earlier systems, the Norden was unmatched. Its accuracy improved circular error from thousands of feet to hundreds, allowing concentrated strikes on strategic targets. Entire industrial centers, ball-bearing plants, oil refineries, and transport hubs could now be targeted systematically. The Norden did not make bombing perfect, but it made it scientific. The device's complexity was astonishing. More than 2,000 components, gears, cams, gyroscopes, prisms, and servo motors worked together in harmony. Each bombsight took weeks to build and calibrate. Norden's team and later the Victor Adding Machine Company produced tens of thousands during the war, each costing about $10,000, nearly as much as a fighter plane. Despite its delicacy, it endured vibration, cold, and the brutal conditions of combat flight. It was a masterpiece of mechanical engineering in an age before digital logic. The Norden's greatest triumphs came during the U.S. daylight bombing campaigns of 1943 to 1945. Flying fortresses and liberators carried it over Germany, striking oil depots and transportation lines that crippled the Nazi war machine. In the Pacific, it guided attacks on Japanese shipyards and cities. It was also used on the Enola Gay, the B-29, that dropped the atomic bomb on Hiroshima, linking the Norden indirectly to both the technological zenith and moral weight of the air war. But the Norden bombsight was more than a tool of destruction. It represented a mindset. It symbolized faith in calculation, in the belief that engineering could make war rational. It turned bombardiers into technicians, pilots into instruments of precision. Its smooth gears and spinning gyroscopes mirrored a nation convinced that science could control even the chaos of battle. After the war, newer electronic systems and radar-guided bombs rendered it obsolete. But its legacy lived on in every guidance computer that followed. The Norden was the ancestor of precision warfare, the moment when human judgment first fused with mechanical computation. It did not always deliver perfect accuracy, but it changed what accuracy meant. In the cold air above Europe, men peered through its lenses and believed they were seeing the future. A future where mathematics could aim, machines could think, and war itself could be reduced to numbers. The Norden bombsight transformed bombing from instinct to engineering. Yet its story was not only about technology, it was about belief. The United States Army Air Forces built an entire doctrine around the Norden's promise of precision. It was the core of daylight strategic bombing, the idea that wars could be won by destroying the enemy's industrial heart from the air, without the need for costly ground invasions. In theory, the Norden made this possible. American planners envisioned fleets of B-17s and B-24s flying in tight formations, striking factories, bridges, and oil refineries with surgical accuracy. Precision daylight bombing became both strategy and propaganda. The bombsight was its talisman, the instrument that made moral warfare conceivable. If bombing could be precise, it could also be justifiable. In practice, reality was harsher. Clouds, anti-aircraft fire, wind drift, and pilot fatigue all conspired against accuracy. Even with the Norden, only about 20% of bombs landed within 1,000 feet of their targets. Still, the device gave commanders something no other air force possessed: confidence in the possibility of precision. The British, after suffering heavy losses in early raids, turned to nighttime area bombing, blanketing cities to crush morale. The Americans, armed with the Norden, insisted on daylight attacks aimed at specific industries. This division of philosophy shaped the Allied air war. The Norden became more than a tool. It was the hinge between two different kinds of war: destruction by calculation versus destruction by saturation. Technically, the bombsight's genius lay in its stabilizing gyroscope and analog computing system. It corrected for aircraft pitch, roll, and speed, continuously updating the angle of attack as the bombardier tracked the target. Its interface, a set of knobs, dials, and crosshairs, was intuitive enough to operate under stress, but complex enough to demand months of training. A single mistake in calibration could send bombs miles off course, so bombardiers were treated as elite technicians, sworn to secrecy and precision. They wore sidearms, not for combat, but to protect or destroy their equipment if captured. Manufacturing the Norden required microscopic precision. Each sight was hand-assembled in clean rooms by technicians trained like watchmakers. Calibration took days. Testing took weeks. The resulting machine looked almost delicate, but in flight it endured vibration, freezing air, and the shock of bomb release. It became a symbol of mechanical discipline, the idea that reliability could be engineered, not improvised. As bombing campaigns intensified, the Norden's limits became clearer. Weather over Europe often obscured targets. Smoke from previous raids blinded optics. Turbulence disrupted calculations. Engineers responded by integrating radar and improved autopilot systems. The Norden remained the heart of the process, but now worked as part of a larger electronic ecosystem, the beginning of modern integrated targeting systems. By 1945, it had evolved from a single bombsight into an entire philosophy of warfare. It gave birth to an industry that believed in precision as destiny, that machines could remove uncertainty from war. Even when its accuracy fell short, its influence endured. It changed how nations built, planned, and justified aerial power. The Norden bombsight was both a marvel and a myth, a promise of perfect accuracy in an imperfect world. It taught engineers to chase precision beyond the limits of weather, fear, and chaos. And in doing so, it laid the intellectual groundwork for everything that followed: guided missiles, laser targeting, and the digital navigation systems that would someday make its spinning gyroscopes obsolete. The Norden bombsight's legacy was measured not just in missions flown, but in the transformation of how nations conceived warfare itself. Before it, bombing was guesswork. After it, bombing became data. The Norden had fused mathematics, optics, and human judgment into a single instrument, the prototype of modern machine-assisted warfare. Its influence stretched far beyond the skies of the 1940s, shaping technology, ethics, and the philosophy of control in the atomic age that followed. When the Allied air campaign reached its peak in 1944, thousands of bombers carried the Norden into battle every day. Each bombardier's compartment became a miniature observatory, glass, steel, and spinning gyroscopes guiding destruction with scientific detachment. Over Germany, oil refineries, ball-bearing factories, and rail hubs were struck with unprecedented consistency. Though the precision was never perfect, the sustained pressure shattered production lines and paralyzed the enemy's mobility. The bombsight had become a weapon of attrition by calculation, multiplying the effectiveness of each sortie through organization and measurement. In the Pacific, it played a different role. The vast distances and unpredictable weather made traditional navigation nearly impossible. The Norden allowed long-range bombers like the B-29 to aim through cloud and turbulence, relying on optical stabilization and integrated autopilot. Its use on the Enola Gay over Hiroshima and later the Boxcar over Nagasaki gave it a grim immortality. The device that was meant to make bombing humane became the instrument that delivered the most destructive weapons ever built. Precision, once a moral argument, now carried the weight of apocalypse. After the war, the bombsight became a victim of its own success. Radar, electronic navigation, and digital computation quickly surpassed its mechanical limits. But engineers who had mastered the Norden's delicate synchronization of gears and gyros carried their expertise into new fields. The same principles guided early analog computers, fire control systems, and missile guidance units. The lineage from Norden's hand-cranked mechanisms to the first digital targeting computers was direct and unmistakable. Culturally, the bombsight came to symbolize both the promise and the peril of scientific warfare. It embodied faith in control, the belief that human reason could manage destruction with precision. Yet the devastation of Dresden, Tokyo, Hiroshima, and Nagasaki exposed the illusion of clean war. The Norden had narrowed the margin of error, but not the moral distance between calculation and consequence. Its crosshairs, once symbols of mastery, now looked like questions. By the 1950s, most Norden sights were decommissioned, stored, or sold as surplus. A few found their way into museums, silent relics of a mechanical age that believed perfection could be built with gears. Yet every modern guidance system, from cruise missiles to GPS bombs, carries its DNA. The gyroscopic stabilization, predictive computation, and automation that defined the Norden remain the foundation of precision warfare. Carl Norden himself never saw his invention as a weapon. A quiet engineer, he considered it a tool for minimizing civilian casualties, not maximizing efficiency. He died believing he had made war more humane. History, however, gave his creation a more complex verdict. The Norden bombsight had not made war precise. It had made precision an ideal, one that the world would forever pursue, never fully reach. In the cold air above Europe, the hum of gyroscopes and the turning of gears marked the beginning of a new age. An age where machines could measure the unmeasurable, where every decision could be computed, and where the illusion of control became as powerful as control itself. The Norden bombsight was not merely an instrument of aim. It was the first mechanical vision of total certainty, and the moment humanity learned that even perfect aim cannot guarantee a just target.